All right, let's jump right in. Today we are tackling one of the most fundamental processes in the entire universe, the redox reaction. Seriously, if you've ever wondered how things burn, how a battery powers your phone, or even how you get energy from your food, you're in the right place. Get a grip on redox, and you've basically unlocked a huge chunk of chemistry.
So here's how we're going to tackle this. We're going to start with the old school way chemists thought about these things. Then we'll see where that theory started to, fall apart. After that, we get to the modern view, which is a total game changer. And finally, I'm going to give you a super simple toolkit so you can look at any redox reaction and know exactly what's going on.
Okay, just look at these three things for a second. A rusty nail, a roaring fire, and the battery that's probably powering the device you're watching this on. I mean, they seem totally different, right? One is slow and quiet, one is fast and chaotic, and the other is, well, it's controlled. But believe it or not, they are all driven by the exact same chemical principle. By the end of this, you'll see it crystal clear. Science isn't static, right? Our understanding is always growing and evolving. As we get better tools and make new discoveries, we have to update our models of how the world works. In the story of redox reactions, it's a perfect example of this in action. We had an old idea, and then we found a much, much better one. So let's rewind the clock a bit and look at the classical view. Early chemists, you gotta remember, were working with what they could see and measure directly. So for them, it was all about tracking the movement of specific atoms, mainly oxygen and hydrogen. This view wasn't wrong exactly, it was just incomplete. They were only seeing the tip of the iceberg. And here are those old rules in a nutshell. Oxidation basically meant you were adding oxygen or taking away hydrogen. Reduction was just the opposite. It was a pretty straightforward system, all based on which atoms were physically being shuffled around. And hey, it worked for a lot of the reactions they were dealing with at the time, but it definitely had its limits. As chemistry got more advanced, scientists started discovering all sorts of new reactions. And pretty quickly, it became obvious that the old rules just didn't cut it anymore. It was like trying to fit into a suit you've completely outgrown. The old model was bursting at the seams because it just couldn't explain all the new things they were observing. So what were the big issues? Well, first off, what about all those reactions that had nothing to do with oxygen? The very name oxidation was becoming a problem. Second, the old rules didn't really have a good system for tracking an atom's, let's call it its chemical state. But the real killer, the thing they were totally missing, was the true engine driving the whole process. It was obvious there was something deeper going on that they just couldn't see.
And this led to a massive aha moment. Scientists realized they needed to look past the atoms themselves and focus on something much smaller, the electrons. The real story wasn't about oxygen or hydrogen moving around, it was about the transfer of electrons. Just think of electrons as the universal currency of chemistry. It all comes down to who's giving up that currency and who's gaining it.
So that's the fundamental switch, right? We stopped watching the big, clunky atoms and started tracking the tiny, super important electrons. And this one simple change completely revolutionized chemistry, giving us one powerful, unified way to understand a huge range of reactions.
With this new electron-centric view, the definition suddenly becomes so much simpler. Oxidation is quite simply the loss of electrons. That's it. Think of it like a substance is spending its electron currency. And since electrons have a negative charge, if you lose a negative thing, you become more positive.
Here's a perfect example. We've got a neutral sodium atom. It kicks out one electron. Bam! It's lost the negative charge, so it becomes a positively charged sodium ion. Simple as that. The sodium has been oxidized. And the other side of the coin, of course, is reduction. This is simply the gain of electrons. The substance being reduced is earning that electron currency. And since it's gaining negative charge, it becomes more negative, or at the very least, less positive than it was before. Let's look at chlorine. A neutral chlorine molecule, which has two atoms bonded together, comes along and snags two electrons. Each atom gets one, and they split apart into two separate negatively charged chloride ions. The chlorine has been reduced. And this is what's so incredibly powerful about thinking in terms of electrons. It doesn't matter what you start with, a neutral atom, a positive ion, a negative ion, the rule is always the same. If it loses electrons, it's oxidation. If it gains electrons, it's reduction. It's a universal law. Okay, theory's down. But how do we actually keep track of this invisible flow of electron currency, especially in big, complicated molecules where electrons are being shared, not completely handed over?
Well, for that, we need a special tool for our chemistry toolkit, the concept of oxidation states.
Now, this might sound a little abstract at first, but stick with me. It's basically just a bookkeeping system for electrons. In any chemical bond, we just pretend, for accounting purposes, that the more electron-greedy atom gets all the electrons in that bond. The imaginary charge each atom ends up with, that's its oxidation state. It's a brilliant way to see who's winning the electron tug-of-war.
And to figure these states out, we just follow a few simple rules, kind of like a pecking order. We always start with the most electron-greedy element out there. Fluorine. It's always -1, no exceptions. Then we work our way down the list. Oh, and here's the easiest one of all. Any pure element, all by itself, like a chunk of iron metal or a molecule of oxygen gas, always has an oxidation state of 0.
Now, this next rule is the key that makes the whole system work. Everything has to balance out. For a neutral molecule like water, H2O, all the individual oxidation states have to add up to 0. And for a charged ion like the sulfate ion, they all have to add up to that ion's total charge, which in sulfate's case is -2.
All right, let's put this into practice with sulfuric acid, H2SO4. Don't worry about the structure on the slide, just look at the formula. We know this molecule is neutral, so everything has to add up to 0. Okay, from our rules, each hydrogen is a +1, and we have 2 of them, so that's +2. Each oxygen is usually a -2, and we've got 4, that's -8. So we have +2 and -8. What does the sulfur in the middle have to be to make the whole thing equal 0? You got it. It has to be +6. See? It's just a little puzzle. Now, here's a fun one that shows why sometimes you have to look at the structure. This is a very weird molecule with a cool butterfly shape. Because of that weird shape, some of the oxygen atoms are bonded to each other. That's a special case, and it changes their oxidation state to -1 instead of the usual -2. It's a great reminder that chemistry loves to have exceptions that keep us on our toes. So, let's boil this all down to the one thing you absolutely have to remember. When something is oxidized, it loses negative electrons, so its oxidation state goes up. It becomes more positive. When something is reduced, it gains negative electrons, so its oxidation state goes down. It becomes more negative. Oxidation is an increase, reduction is a decrease. That's the golden rule.
This table really sums up our entire journey today. We went from a limited view based on just a couple of atoms to a universal view based on the electron. We went from just kind of observing changes to being able to precisely calculate what's happening using oxidation numbers. It's a huge leap forward, and it's the foundation of modern chemistry. So let's go all the way back to the start. That rusty nail, the burning fire, the battery in your phone. You see it now, right? The common thread is the movement of electrons. But it's so much bigger than that. The same thing is happening when your body digests food to get energy and when a plant uses sunlight to grow. Redox reactions are literally everywhere, powering our world. So now that you have this key, this new lens to see the world, what else are you going to figure out?